Good morning, good afternoon, and good evening. Welcome back to Chapter 5. We're still talking about transport. We're still talking about how molecules move into and out of the cell. At the end of the second video, we were talking about osmosis. We're talking about our last method of passive transport. Let's finish talking about osmosis. When you've got a cell in water, that water will be one of three possible conditions. It can either have less dissolved stuff in it than the cell does, the same dissolved stuff, or the same amount of dissolved stuff as the cell does, or it has more. And let's stop and pause for just a second. I've got a cell, a living cell. Inside that cell there is mostly water, but we said a couple chapters ago, yes, there's water in there, but there's also stuff dissolved in that water. So it's not pure water inside a cell. There's not pure water inside of you. There's not pure water in your cells. You have water with stuff dissolved in it. So if I take one of those cells and I put it in a beaker of water, if I specifically put it in a beaker of pure water, distilled water, nothing but water, I have now put that cell in what's called a hypotonic solution. Hypo means under or low. Tonicity just refers to the amount of dissolved stuff. So hypotonic specifically means less dissolved stuff. Less dissolved stuff in the water than there is inside the cell. If I have that condition, based on what we know of osmosis, there's more water outside than there is inside the cell. So what happens is water will flow into that cell. And if the difference is big enough, the cell can actually rupture. It can lyse. Lyse means to pop, just like overfilling a balloon, it pops. Iso means the same. So isotonic means the same solute. It doesn't mean it's the exact same stuff. It just means there's the same amount of stuff. So it could be salt inside and sugar outside, but it's okay if it's the same amount. So isotonic means there's the same concentration of stuff dissolved in the water as there is stuff dissolved inside the cell. And a great example of an isotonic solution are eye drops. If you've got eye drops because you wear contacts, what you're dropping in your eyes is called saline, right? Saline is specifically isotonic to what your body is supposed to be. So if your eyes are dry, that means they don't have enough water. So we drop saline in them, which should bring them up to the proper level of water without going over, without taking it too far until it lyses. Your eyes aren't going to pop out of your head if you put fresh water on them. But that is the point of saline, is to hydrate them just enough, but not to overhydrate. Isotonic, same solute. Same solute, if I take a cell, a healthy cell, and put it in an isotonic solution, some water will flow in, but an equal amount of water will flow out. There will still be movement. We talked about that in a couple of videos ago, but there's no net movement. It's that for as much comes in, an equal amount goes out. Our last condition is if we take that cell and we put it inside of salt water. We put it in something that's super concentrated. That's called a hypertonic solution. Hyper means a lot. What's a hyperactive kid like? They're way too active. They have too much energy. Hyper means above or a lot. So hypertonic means lots of dissolved stuff. If I take my normal healthy cell and put it into salt water, now I've got my cell is in a hypertonic solution. And with the hypotonic, remember, the water flowed in because there was more stuff dissolved in the cell. In this case, there's more stuff dissolved in the salt water, so the water will flow out. And that cell will shrivel up. And when a cell shrivels up like that, we say the cell crenates. Here we see pictures. This is a red blood cell. This is what a normal blood cell looks like inside of you. Notice how it kind of looks like a donut a little bit. If I take that normal red blood cell and put it into pure water, it will fill with water. Water will flow into my cell until it pops, until it ruptures. And when we say that, we say the cell has lysed. Isotonic means it's the same amount of solute. So yeah, some will flow in, but an equal amount flows back out again. And the last condition is hypertonic, and that's salt water. And this will draw water out of the cell. And notice how water is moving out. This is what happens to animal cells. Down here is what happens to plant cells. If I give water to a plant that has wilted, the water will flow into the cell and it will turn that cell what's called turgid. And that's when the plant stands back up again. It's nice and healthy. If it has the normal amount, if you give it basically plant version of saline, it will still flow in if it's dehydrated, but an equal amount will go in as what comes out. And last is if I give a plant salt water. If I give it salt water, the same thing will happen to the plant cell as happens to our cells, and that is it will shrivel up. It will lose water. Water will go out. The difference is between a plant and animal cell is if you put pure water in a plant, it will not pop because it has that cell wall around it. The cell wall prevents it from overfilling. If I keep filling a water balloon, it can eventually pop. But if I put that water balloon inside of a wooden box, it can only fill up until the box doesn't let it fill anymore, and then it won't pop. It just stops filling. That's what the cell wall does for the plant cell, is it prevents it from overfilling. There are three methods of transport, three ways in which cells get stuff into and out of themselves. The first way is passive transport, and that doesn't require the cell to spend any energy. And we just finished up talking about passive transport. Active transport does require the cell to spend energy. That's why it's active. Active transport is usually for moving things against the gradient. Let's go back and talk about the bowling ball. If I'm carrying a bowling ball walking uphill, number one, is it hard to carry a bowling ball walking uphill? I mean, is it harder to carry the bowling ball walking uphill than it would be just to walk uphill without it? And the answer is, yeah, it's a little harder. So that means I'm having to spend extra energy to overcome the weight of the bowling ball because I'm taking it against the way it wants to go. If I put that bowling ball on the ground, we already said that, if I'm in the middle of the hill and I put the bowling ball on the ground and let go, what is it going to do? It's going to roll downhill. That's the way it wants to go. That's diffusion down the gradient. With active transport, I'm pushing it against the gradient, against the way it wants to go. So I'm having to spend energy. If I want to take that bowling ball and carry it up the hill, I've got to spend energy to force it to go against the way it wants to go. Active transport. Active transport is for transporting things against the gradient, against the way it wants to go. Our first version of active transport is called primary active transport. AT just stands for active transport. Primary active transport moves things directly against their gradient. A good example of it is the sodium-potassium pump. The sodium-potassium pump they're located all around your cells, specifically like your muscle cells and your nerve cells have the sodium-potassium pump. The sodium-potassium pump is a special channel, and this special channel moves things against the way they want to go. And the way they want to go is, I've got my cell. What the sodium-potassium pump does is it moves sodium out of the cell. And so outside my cell, I've got 10 or 20 times as much sodium outside as I do inside. Lots more outside. How did it get there? The pump puts it there. The pump pushes sodium out. If you look at this, which way was the sodium going to want to go? Is it going to want to go out? Diffusion says what? Diffusion says if I have a lot of it here and not much of it there, it wants to go from where there's a lot to where there's not much. And so the sodium wants to go in, but which way does the pump push it? The pump is pushing it out. My other ion is potassium. Potassium is the opposite, and it is 10 or 20 times more concentrated inside the cell as it is outside. And again, what does diffusion say? Diffusion says if I have a lot of it inside and not much of it outside. It wants to go from where there's a lot to where there's not much. How did it get this way? The way it got this way is that the pump pushed it in. Any potassium found outside gets pushed into the cell. Any sodium found inside gets pushed out. And the pump, you have to actively spend energy to run this pump, because which way does the sodium want to go? The sodium wants to go back in. Which way does the potassium want to go? The potassium wants to go out. And the only reason why they're in this condition here is because the pump put them there. The pump forced the sodiums out when they wanted in, and the pump forced the potassiums in when they wanted out. This is primary active transport. Secondary active transport works off of gradients created by primary. So, does sodium want to get back in? And the answer is yes, sodium wants back in. What the cell does is the cell gives sodium another way to come back in. And this is a back door. But sodium can only operate this back door if it brings sugar with it. This is the sodium glucose pump. Why does sodium want to go in? Well, because it's forced out. So the cell forces the sodium out to make it bring sugar back in with it. And what is the cell going to do with the sugar that comes in? The cell's going to eat that sugar. The only reason why sodium wants to come back in is because it's been forced out. The sodium-potassium pump is primary active transport. The sodium-glucose channel is secondary active transport. The only reason why sodium wants to come back in is because it's been forced out to begin with. If we look at this right here, we see how active transport works. We've got a few of them inside, we've got several of them outside. One of them flows into my channel protein. I have to actively spend energy to force these to go out. Now I have put even more outside than what I have inside. I'm forcing them to go against the way they want to go. Active transport. You have to spend energy to force molecules to move against the way they want to go.